All right, so the topic for today is going to be, in depth into the Poisson distribution, and most importantly, we're going to talk about the Poisson approximation for balls and bins, and an important process known as, it's kind of like a trick for analysis, an algorithmic and analysis trick called Poissonization. Okay, so this is sort of the main topic for today. So let me begin by just recapping this the balls and bins setting. So you have the balls and bins setting, and what I'd like to talk about is actually a more general situation where each bin. So sorry, someone needs to mute. So let me just mute everyone here. Costas, I think you need to mute. Hang on. Okay. Yeah. Okay. Sorry about that. So I just muted everybody here. Okay. So doing balls and bins. So each bin has a different probability pi. So I should say the ith bin has the probability pi. So in in terms of statistics, this is just called these are called, this would be draws from what's called the categorical distribution, which is, we're just looking at an arbitrary discrete distribution. Okay, so it's an arbitrary discrete distribution, and if so, we have n bins and m draws or balls. So the bins are simply n outcomes, right? So each bin is a different outcome, and each ball is just a draw. And so the distribution has a name, is the multinomial. So this is the multinomial distribution, which is m draws from a categorical distribution. A categorical distribution is simply, there are n outcomes. The ith outcome has a probability of pi. And so if you look at the number of balls in the ith bin, this is distributed as a binomial m comma pi. M is the number of draws. Now, I think it's useful to just recount the Poisson distribution and sort of the Poisson, where the Poisson appears. So note that, so we can say the probability. So let me refer to this random variable as xi. So what is the probability that xi is equal to k? And what we have is, it's m choose k because there were m draws, pi to the power k, and 1 minus pi to the power k. I'm sorry, thank you, m minus k, right? 1 minus pi to the power m minus k. Okay, so let's think of mpi as a constant. So I'm just going to run some approximations here. And I just want to think of MPI as a constant. So M is a very large number and PI is a very small number. And so what I get is that this would be approximately m to the k divided by k factorial, right? This is just approximating the binomial coefficient times pi to the k times e to the minus pi times m minus k, right? So I'm just doing 1 minus pi as e to the minus pi. And again, since m I want to think of is going to be much larger than k, right? I'm looking at the situation where I get k successes, where really the probability of each individual success is very small. It's like 1 over m. So this is the expression that I get. So I can, approximately I can just ignore this minus k here. And what I get is, I guess, pi times m to the power k divided by k factorial e to the minus pi times m. Let me just zoom out a bit so that I can, okay, there, okay. So note that what we have here is that this pi times m appears. So we can write this as mu to the k e to the minus mu divided by k factorial, where mu is pi times m. Or I should have written this as pi times m, right? And so this is the expected number of successes. So mu is the expected number of balls that will fall in the ith bin, and the distribution is approximated by mu to the k e to the minus mu divided by k factorial, and this distribution is the Poisson distribution. So the Poisson distribution it's a discrete distribution where the probability of y equals k is going to be mu to the k e to the minus mu k factorial, and this is also denoted by Poisson. So there's one parameter. That parameter is mu, and this is discrete. So this is for all k in basically natural numbers, union 0. Okay, so this is a discrete distribution that takes on all non-negative integers, and the distribution is given exactly by this expression, mu to the k e to the minus mu divided by k factorial. But to give you some intuition behind why this formula appears, if you look at the balls in bin setting, then the Poisson distribution is a good approximation of the number of balls that fall into the ith bin, assuming that the expected number of balls that falls in the bin is constant. Okay, so this is the Poisson distribution. Okay, so now let's go back. So actually, let me let's now investigate the Poisson distribution a bit, and then once we do this investigation, let's just discuss the basic properties of the Poisson distribution, and I'll use y to denote the Poisson. X's are going to denote the balls and bins. So the Poisson has a number of very nice properties. Okay, and in many ways one can think of it as a discrete version of a normal random variable, because it satisfies many of the properties that normal random variables satisfy. So firstly, the expectation of y, where y is again distributed as a Poisson with parameter mu. Y is the expectation of y is mu. The variance of y is also mu. So I'm not going to prove these. These are calculations that I leave to the scribe. But let's get some understanding of what this distribution looks like. So what is the probability? Let's start with just the probability that y being exactly its expectation. So let's think of mu as a sufficiently large constant. Let's think of mu as a sufficiently large constant, so that's going to be convenient. So if I plug in the formula, what is the probability that y is equal to mu? I get e to the minus mu, and remember the formula that I got was mu to the k divided by k factorial, but I'm thinking of k is actually mu. Think of mu as a sufficiently large constant, and also think of mu as an integer. I'm doing these calculations just to give you some intuition. So I'm going to use lots of approximations but these approximations will be correct, when mu is a sufficiently large integer, when mu is sufficiently large. If mu is not an integer, then you could basically replace this by the floor of mu. Okay, you can replace this by the floor of mu. Sorry, just fixing my camera. Okay, so e to the minus mu to the mu divided by mu factorial. Right? This is the probability that you get. Now, a very important approximation is Stirling's approximation. So what Stirling's approximation says is that, or I should say, instead of mu, I should say k factorial is essentially equal to square root of 2 pi k divided by e to the power k, 1 plus little o of 1. And that little o of 1 is something that goes to 0 as k goes to infinity. Right? So this is square root 2 pi k divided by e to the power k is a good approximation of k factorial for sufficiently large k. So let's go ahead and plug this approximation in over there. I'm going to ignore the little o of 1 term. So I'm going to write this out as approximate. So what is the probability that y is exactly equal to the mean? So this is going to be approximately e to the minus mu to the mu divided by square root 2 pi mu to the mu e to the minus mu, right? Because this is mu to the mu e to the minus mu. So I get exactly the numerator over there. And so what I have is this is theta of 1 divided by the square root of mu. This is a very important fact to know. So the probability that a Poisson takes exactly its mean excuse me, is 1 divided by the square root of the mean. Okay, now let's go one step further. What is the probability that y is going to take the value mu plus delta for some delta that is smaller than mu? So I'm looking at deviations around mu. I'm looking at the probability that that y is going to take, the Poisson is going to take exactly the mean plus some deviation. And you can think of this could even be a negative deviation, right? So I'm thinking of just the absolute value being less than mu, and I'm looking at negative deviations as well. I'm going to plug in this approximation, and actually I get something that is quite interesting. So I get e to the minus mu to the power mu plus delta. Remember, it's mu to the k divided by k factorial. That is k. Mu plus delta factorial. Again, this is an equality. Now applying Stirling's approximation again, e to the minus mu to the power mu plus delta. This is going to be a little. It's going to be a little bit of algebra that we need to do here. I get square root 2 pi mu. Then I get mu plus delta to the power mu plus delta. And e to the minus mu plus delta. Okay. Now let me move things around a bit. The e to the minus mu and e to the minus mu will cancel. So I get an e to the delta in the numerator divided by, and let me write this out as square root 2 pi mu times the square root of 1 plus delta divided by mu. Right? I'm just expanding that out as this. Times, I'm just going to combine these together. I'm going to get 1 plus delta divided by mu to the power mu plus delta. Okay? So all I did was I took this part, the mu plus delta to the power mu plus delta, divided it by the mu to the power mu plus delta, and this is the expression that I get. Why did I want to pull this out? Because I want to compare the probability that y is equal to mu plus delta with the probability that y is equal to mu, just to understand how the deviation affects the probability. So I know that when y is equal to mu, it's actually theta of 1 over root mu. Is there any questions at this point? Okay. So what do I get here? So I get this term here, right? This I get times, of course, that quantity. So I'm trying to compare with this times e to the delta. Now I'm going to replace the 1 plus x with e to the x. So I get e to the delta by mu times mu plus delta. This is going to be exactly equal to e to the minus delta squared divided by mu. This looks a lot like the expression for a Gaussian. Remember, because the variance of a Poisson is also mu. And so what you get by this is if delta is less than square root of mu, then this quantity is going to be at most a constant. Then you get the probability that y is equal to mu plus delta is again going to be theta of 1 divided by square root of mu. Right? Because if delta is going to be less than square root mu, you get this dominant term. The second term is just a constant. The third term is also just a constant. The moment delta starts deviating much more than mu, then you start getting a tail bound. And that tail bound is exactly what you get in the Chernoff bound. You can apply the Chernoff bound, and this is exactly what you'll see. So this is very important fact about Poissons. So the idea is the deviation, again, this is assuming that mu is a sufficiently large constant. Obviously, if mu is equal to 1 or 2, the Poisson distribution is well defined, but this doesn't really help you much. But you should think of in the situation when mu is large. So you're doing balls and bins, so that in a particular bin, the number of balls is going to be at least some constant, the expected number of balls. Then you get a behavior of this form, meaning that if you look at the Poisson distribution, remember, the Poisson distribution is non-negative. So here is mu. And what you have is you have a fair bit of probability mass in mu plus minus square root of mu. Okay, so this is, and of course, if you go far beyond, you start getting a tail bound. Now over here, of course, the story is more complicated because you won't get a tail bound all the way, but you'll get some kind of tail bound up to some points, and this is exactly what the multiplicative Chernoff bound with the Poisson with Poisson trials gives you. So any questions about that? So this is a really important fact that I want you to sort of just remember. Like even if you don't remember the calculations, this is important. Any questions? We use the largest of mu for the Stirling for Stirling. Exactly.
So that is the only reason why we get
Exactly, because if you think of if mu is actually close to 0, then you won't have this sort of symmetry around, around this region of square root of mu. The point is, of course, that you want square root of mu to be significantly smaller than mu, which will only happen when mu is a sufficiently large constant. And in any case, I'm putting lots of thetas in places. I'm also doing, this Taylor approximation of replacing 1 plus. Well, okay, this I guess will always hold, but this approximation, will start degrading when delta divided by mu is very close to 1. So, but that'll only affect the constant. That's only will affect the constant. But it's primarily for Stirling. So what this tells you is, roughly speaking, if you just look at what's going on there, look at mu over here. That is, in this window of root mu, there's some omega of 1 probability mass here. And over here, there's also an omega of 1 probability mass. Right? So the probability of being in here and the probability of being in here are both omega of 1 by these approximations. And this is an important fact that we are going to use in our subsequent calculations. Okay, any questions? Okay, so this is.
Is there a reason you can't say it's theta of 1?
I mean, it's always theta of 1, right? Because the probability is at most 1.
Sure.
So I'm just saying that the probability is lower bounded. There's at least some probability mass less than mu. There's at least constant probability mass more than mu. I mean, I could say theta of 1 as well, but to me, the important point is there's a lower bound. There's always an upper bound. Okay. So that is the basics of the Poisson distribution in terms of its behavior. Then we come to our second important fact about the Poisson distribution, and that's a theorem that just says sums, or I should say sum of independent Poissons, the sum of independent Poissons is distributed as a Poisson. And indeed, if you look at the summation of yi, I going from 1 to n, where yi is distributed as a Poisson with parameter mu I, then the sum of yi is distributed as a Poisson with the sum of mu i's. Okay. Of course, the fact that the expectation is correct is easy. That's just linearity of expectation. But what is harder, or what is the magic of the Poisson distribution is that the sum of independent Poissons is distributed as a Poisson. Note that in the continuous case, you would say the sum of independent normals is distributed as a normal. So this is where a Poisson is in some sense a moral equivalent of the normal for non-negative discrete random variables. So the proof, I'll prove it for 2. I'll prove for a sum of 2 Poissons, because I think that that math is worth seeing, and then you can just do induction on top of that. So I'm not going to do the induction for general sums. So let's look at what is the probability that yi plus y2 is equal to k. Right, and I can write this as the sum over all k1 less than equal to k, between 0 and k, of the probability that y1 is equal to k1 and the probability that y2 is equal to k minus k1. Right, and this is where I used independence. Right, I used independence because I broke this. I broke the probability that y1 is equal to k1 and y2 is equal to k minus k1 as the product. Now I can just, run through the math. I get e to the minus mu1 times mu1 to the k1 divided by k1 factorial times e to the minus mu2 to the power k2 divided by k2 factorial. I'm sorry, not k2, but k minus k1. K minus k1, sorry. Now you start seeing what's going on. So you get e to the minus mu1 plus mu2. These terms here do not depend on k1 and k2. Get k1 is equal to 0 divided by k, and I get mu1 to the k1, mu2 to the k minus k1 times k1 factorial, k minus k1 factorial. I'm just going to divide by k factorial here, plug in the k factorial here, and what I get is a binomial coefficient. So I get e to the minus mu1 plus mu2 divided by k factorial, the sum of k1 going from 0 to k, of k choose k1, mu1 to the k1, mu2 to the k minus k1, and you see that this is exactly the expansion of mu1 plus mu2 to the power k, and so you get e to the minus mu1 plus mu2, mu1 plus mu2 to the power k divided by k factorial, and this is exactly the probability of a Poisson, or the probability that a Poisson takes the value k, where it's just where the parameter is mu1 plus mu2, right? And so that sort of ends that theorem. And so for the purposes of this lecture, I think the important facts you need to know about the Poisson are basically that the sums of independent Poissons is distributed as a Poisson, and of course the fact and the behavior of the Poisson around its mean. There are also many other nice properties you can show using the moment generating function. You can prove tail bounds for the Poisson that look exactly like the Chernoff bound. No surprises there, because one is actually trying to approximate the sum of Poisson trials using a Poisson. But now let's go back to balls and bins. So with this detour into the behavior of Poissons, let's go back to balls and bins. And so which again we thought of as M draws from the categorical distribution, or M is basically drawn from a multinomial. Right, so multinomial is just a fancy term for saying you do M draws, or you do some number of draws from an arbitrary discrete distribution. Okay, so we did M draws, and again I'm going to switch between saying draws and balls, but I really mean the same thing. So let's fix M here. Let's fix the distribution P1, P2 to Pn. And let xim be the number of balls in the ith bin when m balls are thrown. Let yi of m be distributed as a Poisson with parameter mpi, which is the expected number of balls. And so the main question is, you have this one vector of random variables x1m, x2m, up to xnm, which is your balls and bins experiment. And you have, and I should say these are all independent. So the yi's are independent. So actually, let me write this in a separate page. Let me write this in a separate page. So we have x1m, x2m, up to xnm. This is describing the balls and bins outcome. So naturally, these are all, they're correlated. These are not independent random variables. Each of them individually comes from a binomial, but they're all correlated, right? And just recall that xi of m can be thought of as a draw from the binomial mpi. Let's think of an alternate experiment, which is y1m, y2m, up to ynm. These are going to be independent draws where yi of m is distributed according to a Poisson with the same expectation. So the expectations are the same, but this is a binomial, this is a Poisson. These are independent Poissons. These are correlated binomials. And the question is, how do these relate? Now, this is a very common sort of way of thinking in the analysis of randomized algorithms, or I guess in general in probability theory, which is you have some sequence of random variables that you care about, except they're a little hard to analyze because of correlations, and because you may not have nice closed form formulae for the distributions. You can write out the closed form formula, and but when you start manipulating it, it's a lot more easier to manipulate the formula for a Poisson directly. And here the Poissons are independent, so often you'll take a sequence of random variables, massage them to get convenient random variables, where convenience often translates to independence and nice formulae for the distributions. So this is going to be now that we've done all this setup, this is going to be the focus of our lecture. How do we relate these? And we'll see that there are actually very nice relationships that often, if you need to do a balls and bins analysis, you can replace them all by independent Poissons, and then the math becomes significantly easier. Okay, so any questions so far? Any questions? Okay.
Clarify?
Yes. Yes.
So the Poisson yi to the m have the same expectation as the xi to the m?
That's right. So the expectation of xi to the m is again m times pi, right? Because you're doing m coin flips where the heads probability is pi, the success probability is pi, expected number of successes is mpi. And of course, that is the only similarity. But another thing to is really, when you have a binomial mpi where, let's say, pi m is fixed to some mu I, and if you take the limit as m goes to infinity, this limit is actually the Poisson. So does this make sense? So it says that if you're taking sort of a sequence of distributions, like I don't want to get into the exact mechanics of the convergence, and that is not particularly important for us, but what you have is you can look at the limit where you're doing a number of coin flips that is going to infinity. So m is going to infinity, but the head success is decreasing inversely in m. in such a way that the product is exactly equal to a fixed constant mu I, then the limit as m goes to infinity gives you the Poisson. Does that make sense? And in some sense, the math that we showed earlier, I actually just gave you the limit, even though I used approximations. And if you sort of work through the approximations, you can prove this using the math that I did earlier.
All right. Professor, I had
Yeah.
a question.
Yes.
So you said that this only applies in the limiting case, right? So we can't really change the model from correlated xi's to independent yi's
So
unless we know that n is very large.
So good question. So this is exactly what I'm going to come to. We'll actually show that this approximation is good even in the finite case.
Okay.
So yeah, I mean, I used the limiting case to show you the intuition. But we will see that actually even in the finite case, we can say lots of very interesting things about replacing the correlated binomials with the independent Poissons. You're absolutely right that the way I set this up, I said, oh, consider the limiting case where m is going to infinity and pi is actually going to pi is sort of inversely decreasing in m. But we'll see that we don't need to make any such assumptions for the subsequent approximations in the math. So let me start.
One
Yeah.
thing. So you said that PIM is equal to mu I, right?
Yes.
Actually, stronger than that, right? We just converging to mu I.
I'm sorry, say that again.
Does it like is there a different version of this? Because I might be making a mistake, but I thought these sequences converge to some finite limit, and it's
Which
not necessarily equal.
which sequences? These.
The PIM.
The PIM. Sure, you can do stronger versions of this where PIM is actually converging to some limit, but I don't think any of that math is going to be directly relevant for what we're going to do. But you're right. You have more stronger versions of this where PIM itself may be converging to a limit, and then you would get the Poisson of that. Yeah. Okay, so let's go to our first important, well, theorem in showing the relationship of the Poisson approximation. And actually, I should maybe say that this conversion that we're talking about, this is the Poisson approximation. So the first property we have is what I'll call conditional equivalence. So conditional equivalence says the distribution YIM Y2M up to YNM. So this is your Poissons conditioned on the summation of YIM, where I is going from 1 to n. So conditioned on this being case. So if you condition on these independent, you did these n independent Poisson draws, condition on the fact that the sum is equal to k. So this conditional distribution is the same as x1m, x2m up to xnm. Okay, so I'm going to sort of pause. I want you to understand what this theorem is saying. This is a balls and bins I'm sorry, I should say K over here. K. My apologies. So this is saying you're doing a balls and bins experiment with K draws. The first part says you're drawing these Poissons, these n Poissons, according to these parameters, and you condition on the sum being equal to k. So note that there's no dependence on m over here. There's only a dependence on k. And here, there's both an m and a k. There's both an m and a k over here. Okay, does this theorem make sense? So it says if you condition on the total sum of the Poissons being k, this is exactly the same as doing a balls and bins experiment with k balls. Okay? So let's do the proof. It's a nice, sort of even demonstrating even more sort of the beauty of the Poisson distribution. So let's look at the probability. Let's look at the balls and bins experiment, where x1, k, x2, k, xn, k is equal to k1, k2, up to kn. And of course, we're assuming that the summation of ki is equal to k. So you're looking at what is the probability of a specific outcome where the sum is k, because this would be a balls and bins experiment. And this is basically, it's this sort of binomial coefficient, or I guess this general binomial coefficient, where you did k draws. So choose k1, k2, k3 up to kn. So you're choosing which of the draws led to which bins times the probability I going from 1 to n of pi to the power ki. You can write this as k factorial times the product of I going from 1 to n of pi to the ki divided by ki factorial. And now this is looking awfully close like what you would see in a Poisson. Right? So this is the expression for, so in this case there is no conditional probability. Okay. Now let's look at what is the probability of y1m, y2m up to ynm being equal to k1, k2 up to kn, conditioned. Now this is conditioned on the summation of yi m, I going from 1 to n, this is equal to k. Right? So this is the conditional probability, which I will simply write as the probability of y1s being equal to the k's divided by the probability that the summation of yim, I going from 1 to n, is equal to k. Right? So any questions? Is clear? Now the denominator, remember that we just proved that the summation yim, I going from 1 to n is distributed as a Poisson with just the summation of parameters, which is m summation pi, I going from 1 to n, but this is just 1. So this is distributed as, this is the same as just the distributed as a Poisson with parameter m. Now, for now, you're going to have to sort of ignore the asymptotics I discussed. There's no asymptotics here. This is an equality. And this is where I use the fact, this is using the balls and bins. So the summation of pi has to be 1, right? Because each ball has to go into some bin, and so the sum of probabilities of each of the bins is 1, right? This is just saying it's a distribution, and therefore summation of yi of m, which is the sum of all of these individual Poissons, is distributed as a Poisson with parameter m. We're going to come back to this fact later on because this is going to be the heart of what's called Poissonization. So we know how to deal with the denominator here. The numerator is also easy now because this is the probability of a vector of independent Poissons taking some vector of values, and we can break it up as the product. So what I get for this probability, so this is the probability that, y1m up to ynm is equal to k1, k2 to kn, conditioned on summation of yim is equal to k. This I can write now as the product, I going from 1 to n, of the probability that yim takes the value ki times, there's no product over here. This is just the probability that the summation of yim is equal to k. Now I just plug in all the various formulas. So the numerator I get I is going from 1 to n, e to the minus mpi, mpi to the power ki divided by ki factorial. And in the denominator I get e to the minus m, m to the power k divided by k factorial. Now move everything around. What you'll see is that this cancels out with all of this, and that's because the summation of pi is equal to 1. The m to the k will also cancel out with the m to the k over here, because what you'll get over here is you get m to the minus summation of pi divided by e to the m times m to the summation of ki divided by m to the k times what we had seen earlier. You'll get k factorial times product of I going from 1 to n of pi to the ki divided by ki factorial. Now these just cancel out, and this is precisely the probability that we saw earlier, and so this is the probability that xik to xn of k is equal to k1 to kn. And so what is magical here is that when you do this conditioning, the dependence on m disappears. Right? Even though the Poissons involve m as their parameter, when you condition on the sum, the dependence on m disappears. Okay, so is that clear? Any questions on that? So again, if you got lost with some of the manipulations in the proof, you can go back and look at them. There's nothing particularly fancy. You're just writing out all the expressions explicitly and cranking through the math of the Poisson distribution. What is important is that the conditional distribution of these independent Poissons is exactly the balls and bins experiment.
So basically this is saying that the only problem with using the Poisson distribution is that you might wind up with more balls or fewer balls than there actually were.
Exactly. Exactly. And this, sort of jumping ahead, this is the heart of the Poissonization trick. So the Poissonization trick says instead of choosing your balls exactly, choose them according to a Poisson distribution, and then you automatically get independence. So we will actually, sort of use the converse of that. But for now, let's go back to why is this going to help us relate these distributions. And now let me prove an immensely powerful theorem. So let f of x1 to to xn. So think of this, x1 to xn are the outcomes of the balls and bins, and you're looking at some function which is non-negative, such that the expectation of f of x1 to the m, xn to the m is monotonically non-increasing or non-decreasing, doesn't matter, in M. So f is a non-negative function such that the expected value of f under the balls and bins experiment is monotonically non-increasing. So for example, a simple case is that f is the indicator for an event whose probability increases or decreases with m. Right, so think of an indicator for an event such that the probability of the event will only increase or decrease if you increase m. And so this covers like coupon collector like situations, coupon collector, maximum load, birthday paradox. And I want to sort of focus on max load. We're trying to say, let's say the maximum load is at most something. This probability is only going to decrease as you increase m. Okay, so this is a very simple scenario of f being the indicator for an event. But in general, you can take any non-negative function. And now I'm going to show you what, at the face of it is an immensely powerful theorem. And this is a stronger version of the Poisson approximation. So the Poisson approximation just directly says that the expected value of the f of x1m up to xn m is at most 2e times the expectation of f going from y1m to ynm. So what this says is you have some event, let's say you're looking at an event whose probability increases or decreases with m. And you can look at the probability of that event in the balls and bins case, or you can look at the probability in the Poisson case. If you get a tail bound in the Poisson case, you will get a tail bound in the balls and bins case. So typically think of the event is a low probability event. You're trying to prove an upper bound on the probability of an event in the balls and bins case. You go ahead and prove an upper bound on the probability in the Poisson case, which is easier to analyze, and you automatically get an upper bound for the balls and bins case with some extra constant. And this is the Poisson approximation. If you have an arbitrary function, I'll just note that if f is arbitrary, then this is replaced by some theta of root m term. So you get actually a dependence on m, but root m is not that big. If you think about trying to get probabilities, if you're trying to prove tail bounds where the probability goes down exponentially in m, then the root m is actually not that bad, or even polynomially in m. I should say polynomially in m, not exponentially. But as long as you can get a tail bound over here which is less than 1 over root m, then you'll get some non-trivial bound over here. So does this theorem make sense? The proof is actually fairly straightforward once you use the Poisson approximation. this doesn't say any. Well, what you can do is you can look at the indicator for the complement event, and then you will get lower bounds. If you're looking at arbitrary functions, then this doesn't give you lower bounds, but you'll see that typically for the kinds of functions that we're interested in, like if typically we're interested in indicators, and for indicators, that is probabilities of events, you will get lower bounds as well. But the lower bound will be up to a constant. So in some sense, either the upper bound is interesting or the lower bound is interesting. Both of them are not simultaneously interesting because you have a large constant over there. Any questions about this? So let me go ahead and show you the proof, and then we can pause and I can take some more questions. So what is the proof? The proof says, well, okay, let's look at the expectation of f of y1m up to ynm. For convenience, I'm going to just represent this as a vector. I'll just call this the vector ym. And analogously, I'm going to have the vector xm. xm. Okay. So the expectation of f of ym can be written as, break it up into conditional, so k goes from 0 to infinity, of the expectation of the vector conditioned on the summation of yi of m being equal to k times the probability that the summation of yi of m is equal to k. I've just broken up this expectation in terms of all the conditional expectations, where I'm conditioning on the sums of yi's. Now note that this yi of m conditioned on summation y of m equal to k is distributed as the vector x of m, right? So you can, when you condition on the total number of I guess in this case successful trials, then that is exactly a balls and bins experiment. So I can then replace the y's over here, but I can just say the expectation of f of x k. Right? K is going from 0 to infinity times the probability that the summation of yi of m is equal to k. So just to be formal, I'm going to do the proof here. For this proof that I'm going to show, I'm going to assume f is non-increasing, or rather the expectation. I'm going to do the non-increase, the monotonically non-increasing case. So in this proof, I'm going to do the monotonically non-increasing case. I leave the non-decreasing case as an exercise, and you'll see the proof will be fairly, go along exactly the same lines. Okay, now I'm just going to drop everything that is before m. Okay. I have the expectation times the probability that the summation of yi of m is equal to k. Right, so I just dropped all the terms where k is less than m. Then I can just write this as the expectation of fxm, right? And this is the non-increasing the non-increasing in M. Or I should say, am I doing this the right? I should probably say non-decreasing. I'm sorry. So my apologies. I'm doing the non-decreasing case, not the non-increasing case, right? Because what I'm using here is I'm just saying that f(x) of m is a lower bound for f of xk, for k is larger than m, times the probability that the summation of yi of m is greater than or equal to m. This is actually omega of 1. Remember, by the pictures that we drew earlier, you can even show that this is at least a half. And so when you move this around, you'll get the expectation of f of x of m is at most, in this case you actually get better than 2 times e, you just get 2 times the expectation f y of m. And that ends the proof. For the non-decreasing case, you would look at all the terms going from 0 to m. For the arbitrary case, you would look at only the term corresponding to m, and that gives you the 1 over root m, because the probability that the Poisson takes exactly its mean is theta of 1 over root m. And this completes the proof of the Poisson approximation. So I'll pause here, I'll take some questions, and then when we come back I'll actually apply this for the maximum load analysis, and then finally show you what Poissonization is. Maybe I'll just say again for the record that the first inequality in this proof just comes by truncation, just dropping out some of the terms. Again, I should be clear over here that I'm using the non-negativity of f. So the non-negativity of f allows me to basically truncate the summation, and then in the second part I use the non-decreasing behavior by just saying for all k greater than m, the expectation of f of xk is at least the expectation of f of xm. So I can replace all of the xk's with xm's, pull them out of the summation, and then push the summation inside, and then I get the probability that yi of m is greater than m. And again, recall that this is a Poisson. So I'm using the fact that the sum of Poissons is a Poisson. And since this is a Poisson, we can get a bound that it's at least the expectation, and this is at least a half. And if you did the other side, you need the probability that the Poisson is at most its expectation. Again, you'll get some constant probability bound over there. Note that, to go back to this question that was asked earlier, I'm not using any asymptotics here. So I use the asymptotics just to get some intuition, but the math is it works without taking any limits. Okay. So now let me apply this for the balls and bins for the maximum load. So remember, we proved earlier. So now consider the standard the uniform balls and bins. Right, so let's do the uniform balls and bins with m is equal to n. So we showed that the maximum load was at most some constant times log n over log n. And we didn't try to optimize the constant, but in the uniform case, you can get like a constant of 3. You can even improve it to just with the Chernoff bound directly. You can get 3. You can get improvements beyond that. We show the maximum load is less than C log n divided by log n with high probability. Can we show the converse? And we will use the Poisson approximation for that. So let me prove this lemma here. So in the standard balls and bins, the maximum load is at least log n over log n with probability at least 1 minus 1 over n. So with very high probability, the maximum load is at least log n over log n. So this is, I think of this as quite remarkable that we can actually nail down the asymptotics of the maximum load so precisely. So we nail it down, exactly, and it can be nailed down to lower order terms. So let's look at our event. So we fix, remember, m and n are fixed. So the event is, we'll say the load is strictly smaller than log n over log n. Now the probability of the event is monotonically decreasing in m, because clearly if you increase the number of balls, the maximum load is only going to go up. So the probability that the max load is less than this is only going to decrease. Now by the Poisson approximation, the probability in the x world of E is at most 2e times the probability in the y world of E. This is going to be easy to analyze. Because so now the probability in the y world of E is the probability of over the y's that for all I, yi is less than log n over log n. I'm going to refer to this as capital M, just for convenience. So for all I, yi is less than m. But by independence, now the power of the Poisson approximation comes up. I can assume, I know that these yi's are independent, so I will simply get the product of I going from 1 to n of 1 minus the probability that yi is greater than m. Recall, of course, that yi is distributed as a Poisson with 1, right? Because remember, all the pi's are 1 over n, and m is equal to n. So each of the Poisson parameter now is just 1. And I'm going to actually, so I want to upper bound this probability. So I just lower bound this. I actually take a very crude approximation. 1 minus the probability that yi is actually equal to m. Okay. Now what is the probability that yi is equal to m? It's e to the minus the Poisson parameter, which is just 1, divided by m factorial. So it's 1 divided by e m factorial. Plugging that in over here, I get the product, I going from 1 to n, of 1 minus 1 divided by e m factorial to the power n. Now using my favorite approximation of 1 minus x being less than e to the minus x, I get this as exp minus n divided by em factorial. Okay, now stare at this for a while. We're saying the probability that the maximum load is at most m is exponential in e to the minus n divided by em factorial. So of course, as m decreases, the probability is going to decrease as well, right? So this is the expression. Okay, so let's go back to this. So putting it all together, I can say the probability in the x world that the maximum load is less than m is at most 2e exponential in e to the minus n divided by em factorial, right? So if we choose m, such that m factorial. Okay, so let's go back to what we want to show. We want to show the maximum load is at least log n over log n with probability at least 1 minus 1 over n. What we want is to get this to be much smaller than 1 over n. So we need to choose m factorial such that the above property holds. Okay, so any questions? So we need to show that this choice works.
Okay, sure.
So I want to argue why this appears naturally. But you're right, you don't get to choose m, but you think of it as we get this expression. Somehow we'd like to see why is this going to be the best possible out of the bound. And you'll see that when you run that math through, that's the best possible you can get. Okay, so any questions over there? So we know by Stirling's approximation, I can just write this as, I can, if I ignore the root 2 pi, essentially I can say there's a constant root m, so this is just some constant. M by e to the power m. Okay. So what you get is when m is log n over log n, right? So we want to show that if m factorial is small, then this will also be small, and as long as if m factorial is going to be less than n divided by the natural log of n, then we're done. Okay, does this make sense? Maybe you need like a 2e or so. If m is less than n divided by 2e natural log of n, then this quantity is going to be less than 1 over n. And so all it takes is to verify that when m is equal to log n over log n, then m factorial is going to be less than n divided by 2e log n. And you apply Stirling's approximation, And I'm not going to do the full math over here, but just to show you, just to give you an indication of what's going on, it's going to be root log n over log n. And if you apply Stirling's approximation and you crank through the math, you'll get log n divided by e log n to the power log n divided by e log n, which we can write as log n over log n. Just write it as e to this log of that, e to the log of that. I'll get log n minus log n minus 1 times log n divided by log n. So the point is, this log n basically cancels out this log n, and then you get something like e to the log n, 1 minus something e to the log n, and this we can show will be less than n over log n. Okay? I'm not going to walk through the full math, but hopefully you see why the dominant term cancels out here. And I'll say exercise, finish the calculation. Now the whole point is, the point of this demonstration was to show you that using the Poisson approximation, you can take what looks like a fairly complex event, the maximum load being less than log n over log n, and you can replace it using the independence of the Poissons and the fact that we have good sort of closed form formulas for the Poisson, with essentially some calculation in logs that you can finish off. So the final point that the final topic that I want to raise, which now hopefully will be fairly easy for you to see, is this idea of Poissonization. So suppose you wanted true independence among the xi m's, right, which is in the balls and bins setting. We know that this vector x, the distribution of x, the distribution of x of k is the same as the distributions of y of m, with where okay, so this is badly where the summation of yi of m is equal to k. I should say conditioned on, conditioned on. So we know that if we condition these independent Poissons on the sum being k, then this gives exactly the balls and bins. What we'd like to do is to sort of flip this around. Can we get a balls and bins, suppose you're doing some kind of balls and bins experiment and you really wanted true independence. And the Poissonization trick is to say, choose k from a Poisson with parameter m, and then do balls and bins with k draws. Then the number of balls in the ith bin is distributed exactly as yi of m. So you kind of flip this around. You say that does this make sense what Poissonization is? So you want true independence amongst the number of balls that fall into each bin. So you actually choose how many balls to drop or how many draws to make from a Poisson distribution. So you first draw the number of draws. You first decide how many balls to drop according to a Poisson distribution, and then you perform the balls and bins with that number. And sort of lo and behold, what you will get is that in each ball, in each bin, the number of balls is distributed as a Poisson, and they are independent. And you get independence. So I'm not going to write this out as a formal proof statement, but I just want to write it out, sort of semi-formally so that you see what's going on. So let me sort of write this out more clearly. Choose k from a Poisson of m. Consider x1k up to xn k. Then this is distributed. This is distributed as y1 of m to yn of m. And this can be seen using the conditional equivalence, which is simply to say that, y1 of m to yn of m is equivalent to drawing summation of yn of m is equal to k, and looking at the conditional distribution of y1 of m to yn of m conditioned, and looking at the conditional distribution of this, right? So you're drawing the sum, and then you're looking at the conditional distribution. But this conditional distribution, this is x1 of k, x2 k to xn of k. So this conditional distribution is exactly x1 to k to xn of k, which is the balls and bins. And as we discussed earlier, this is distributed as a Poisson with parameter m. So I can rewrite this by saying y1 of m, yn of m is equivalent to k being drawn from a Poisson of m, and looking at x1 of k to xn of k, and this is Poissonization. Now, can sometimes, you keep looking at the math and the magic will sort of elude you. So let me tell you something which if you think about it, really will blow your mind. Think of a coin toss, right? And repeated coin tosses. You can think of this as a categorical distribution with just two outcomes. So n is equal to 2. There are just two bins. There's the heads bin and the tails bin. So the number of heads is distributed as the binomial BMP. The number of tails is distributed as a binomial with m 1 minus p. Both of these are binomials. Both are obviously correlated. Right? Because the sum of these is exactly equal to m in all outcomes. Because you did coin toss and let's say m repeated coin tosses. So you did m coin tosses. The number of heads is distributed as a binomial of BMP. The number of tails is distributed as a binomial of BM 1 minus p. Now, choose m from a Poisson. Or I should say maybe choose k from the Poisson with parameter m. Then the number of heads and the number of tails are independent. And that is remarkable. So it says that if you first decided how many coin tosses to do from a Poisson distribution, and then you look at the number of heads and the number of tails you get, then these are actually independently distributed. They're independently distributed as Poissons. And so this is extremely helpful for the analysis, but really when you think of it in this extreme case, it seems almost magical. It seems almost impossible that this should happen. Because conditioned on any choice of k, the number of heads and number of tails are obviously dependent. I mean, their sum is exactly going to be k. But when you choose k from the distribution, from the Poisson distribution, then they're actually independent. And this can really, throw people off for good reason. But it is, one of the magical properties of the Poisson distribution. So I'll end here. So I think, the main topics, the main things to take away from today's lecture are the behavior of the Poisson distribution, the fact that sums of independent Poissons is a Poisson, the Poisson approximation, and sort of understanding the Poissonization process. So I'll stop here and I'll take questions.